Take it away, Frey.
Fantastic. Thank you very much, and welcome everybody. Thank you for coming and sit with me. The last person just talked about how if you can explain something really complicated in really simple words, or if you can't do that, then you don't know your subject well enough. And that feels like quite a lot of pressure to start this off with. So very briefly, I'm Frey. My background is I did a PhD in quantum cryptography type stuff, related stuff, and then I realised I needed one of those, job things. And I spent a lot of time then in cybersecurity. So I worked at Clarinet for a bit. Some of you will be familiar as a pen tester. And then I went freelance, and that was so that I could spend a bit of time building up and supporting some of the research that I did in my PhD and turning that into a company. We just got investment for that actually yesterday. It got signed off, which is very exciting. Because we weren't sure where that was going to be, I'm here in my own capacity. Anything I say is, views of my own, that kind of thing. But more on that later. So this is the Ladybird book of all things quantum, and we are going to talk a little bit about, I'm not going to assume that you know anything, so we'll do an introduction to cryptography, we'll talk a little bit about quantum physics and how that relates to quantum computers. Don't worry, it's not going to be mathsy, there's a good chance that you won't understand all of it, but my goal is that if you come away from here knowing just a little bit more than you did when you walked in, then that works for me. We're then going to talk about some of the problems that cause this for us and the kind of possible solutions to that as well. So, if you're all sitting comfortably, then. So, cryptography. If you have two friends who want to send a message to each other and they want to do that in secret, then they use cryptography. And a sender can scramble up a message, and the method that they use to do that is called a cipher. And if the receiver knows what those steps are, they can undo the steps to get the scrambled message into text that they can read the original message, and small variations in those steps make it harder for someone else to work out. So the exact combination of steps you might use is called the key, effectively. And the whole process of scrambling the message, that is encryption. Right, some people get the words encryption and key distribution cryptography all kind of muddled up, but they actually have specific meanings. So this is an example of a cipher. This is a Caesar cipher. You have the alphabet across the top, and you want to scramble up the letters by shifting them by a number of spaces down the alphabet. So this A is shifted down to D. So it's shifted 3 spaces along the alphabet. So for this Caesar cipher, we are going to say that the key is shift by 3. It could be by 1, it could be by 1, it could be by 25. There's 25 different options you've got there. And what you'd have is this C here would go to an F, and the R would go down to a U, and so on and so forth. Cool, okay, so that is a Caesar cipher. The number of positions that you're shifting it along by is the key. And if both friends are using the same key to scramble up their message and then unscramble the message, your cipher allows you to do that, that is called symmetric cryptography. And there are some ciphers which use keys that are different, the public key and private key, but they are related to each other, and that is something called asymmetric cryptography. We'll talk about that later. And both friends have to agree what key and cipher it is they're going to use before sending those secret messages, and distributing that key between the two people is key distribution. So very briefly, done a lot of big words here, but cryptography is sending secret messages. Encryption is when you scramble up a message. AES 256, that's an example of a cipher that's used to encrypt stuff. We said cipher. Key is kind of the input that you put into that cipher, the specific variation on steps that you use to scramble it up. Symmetric is when you use the same key on both sides, and asymmetric is when you have different keys, usually public key and private key, but they are related. Fantastic. Very good. Okay, so now I want to do this as a quantum computer. It's not because I used AI to try and generate some images. this is actually a quantum computer. So actually, it's massive. It's, you know, about the size of a person, but the actual bit that does the stuff is right at the very bottom here. The rest of the stuff is just fibres for the lasers and stuff to keep it cool and all kinds of other things like that. It solves new types of maths problems. And they are maths problems that normal computers cannot solve. And it is very, very big, and it can only, at the moment, do very, very simple tasks. So think 1950s computer, size of the room, and doesn't really do very much. You can do some maybe basic multiplication if you're lucky. And it uses quantum physics. So if you take anything away from this talk, anything at all, it is that the word quantum is often really, really badly misused. And all it really means is the smallest possible finite amount of stuff. And it's misused all the time. So this is apparently a quantum of cake pan, the smallest possible finite amount of cake pan. And I would guess that you could probably make one, well, not very well, but with a lot of difficulty that's like a layer of atoms thick, then it would probably be a quantum of cake pan. It wouldn't be very useful to cook things in though. This is the smallest possible finite amount of dry. I'm not sure that's what the marketing people at Schumer were intending when they did this. Scientists make the smallest possible finite amount of leap towards a secure new kind of internet. That one's actually believable, I think. And finally, smallest possible finite amount of soft. What do you really want from your toilet paper? Okay, so when we look at normal matter that's, you know, big, it's very easy to guess what it'll do. If I have a ball and I throw it, there are lots of equations that we can use to predict how that is going to go, where it's going to land. We can predict that very, very well. But when we are looking at things that are the very smallest finite amount, it's very, very hard to figure out what it is they're going to do. And they do some really strange things because it can't go smaller than it already is. So it can behave as though it's bouncing like a ball and rippling like water at the same time. It's a bit of a weird concept to get your head around. And what we see really, really depends on how we choose to look at it. It depends on our perspective. And that is really, really important. So, let's imagine we've got two quantums or quanta here. And at the minute we're looking at them from like the top-down perspective, okay, and we see them as two separate blobs. But if we want to look at it from the other dimension, and we spin those around, that went very quickly, all of a sudden, as we are looking through, we see both of them kind of superimposed on top of each other. And that is something called superposition, where they're both kind of, they're not necessarily operating as independent things anymore, and they're doing some kind of weird stuff. And again, this is all because we changed our perspective. So, quantum things as well, like I said, they're the smallest it can possibly get. And that means that you sometimes have related properties. So if you imagine you've got a ball, and the ball, you can't take any material away from it or add any material to it, but you can squash it. And as you squash it in one direction, this stuff has to go somewhere, so it goes out in the other direction. It's easy to think about it in terms of physical dimensions, but it also applies to other kinds of related dimensions as well, so energy and time, position and momentum. And the better we try and get at measuring it in one direction, the more kind of flobbly and blurry it gets in the other dimension. And that is something called the uncertainty principle. So if you look at it in that direction, you can squish it down, but it spreads out in the other way. And if we were to then go, right, okay, we'll shuffle around and we'll look at it that way, and then it spreads out in the opposite direction instead. So, when we are looking at something in one direction, we can't really control what it's doing in the other one. And with that, we can only guess how likely it is to do certain things. And we can do that by doing lots and lots and lots of experiments. We take 100 of them and we see what the chances are that it does certain things. And these properties are really, really strange, but we can harness them to do new and exciting things. So, for example, searching problems. So, when we're not looking at a particular dimension of a quantum object, it actually tries to do all of the different things at once. And it only decides what it's done when you look at it in that particular dimension. Sounds a bit strange. And it's more likely to behave in the way that's easiest, but it could do any of them. So if I have 100 things and let's say I've got 100 balls, they're all quantum balls, and I've squashed them all down, I've measured them in that way, and I've not looked at them from the sideways dimension, not looked at them yet, and then I choose one by one to look at them at sideways dimension. Some of them will have squashed to one side, some of them squashed to the other, some of them will be in the middle, and whichever one is the most energetically preferential, the easiest one, is the one that it's most likely to have done, but some of them will have done all of them. So yeah, if we do this just once, it will pick one way at random, but they will statistically add up to bring a pattern towards the end of it that shows the easiest position. So we're looking at it down like that, then we're looking at it at the side this way. So it could be that both of them are quite close together, or it could be that both of them are quite far apart. Some of the times we'll measure this one blob and it'll look like it's quite close together, and sometimes it'll look like it's quite far apart, and that will be governed by some probability. So we can use this to our advantage. If you imagine an object that is going through a maze, it's a quantum object, and if you're not looking at it, it's going to try and go through all of the routes at once. And if you can kind of, suspend reality for a moment and imagine that you can measure it after it's been through the maze, it'll show you, if you do it lots of times over lots of them, it'll show you that it goes through the easiest route the most often. Okay, so we've got two mazes here. This one is a classical object. Please excuse my terrible scribbles. And if you are a classical computer, the only way you can solve this is try all of the different routes. Yeah, no, it's not that one. Let's go up here, etc., etc. I didn't bother drawing in all of the others, but you get the point. And eventually you're like, okay, no, I know it's this way. But if you've got a quantum object, you stand through that maze, it'll go through all of the ones at once, and then when you want to measure it at the end, it'll decide which route it went through. And if you do it with lots and lots of objects, you can build up a position, build up an understanding of which route was the easiest, because that's the one that I've done most often. So, if you've got some quantum-sized things, then it's very easy to find the best route compared with normal classical computers. And there are some maths problems that look like this, called searching problems. Some of them are very famous. One of those particularly famous ones and interesting ones for us is something called prime factorization. Basically, you can take a maths problem and turn it into some kind of search space. We're searching to find the easiest route through this. Some of you might have heard of the travelling salesman problem. That's another searching problem. Even just a simple binary search, actually, it takes quite a long time to search through an entire database of stuff. So prime factorization then, you think of a number, and then you try and find the two, or however many, smallest possible numbers that multiply together to make that big number. So if I give you the number 21, have a think. The two numbers that multiply to make 21, and they don't go any smaller because they don't multiply by any more things, they're prime numbers, are going to be 3 and 7. You were probably able to do that in your head, but for a normal computer, they've got to try basically all of the different possible combinations. They can simplify it a little bit, but it's still quite a tricky problem. And that means that if the number is very, very big, it gets exponentially more difficult to do. So if if I gave you the number 5105, that's probably very difficult to do. But if I tell you that one of those numbers is 1021, suddenly it becomes a lot easier. And you can figure out that the other number is 5. So what we can do is we can kind of make this like a public key. So I'm going to give you the big number, but you can't figure out what my private key is, my 2 small numbers are, unless you already know what one of them are. So my private key is a little bit like 5 and the 1021. I've grossly oversimplified this. It's a lot more complex in practice, but basically the public key and the private key are linked together by a difficult maths problem like that. And the public key is kind of like the instructions for someone to encrypt the message, and you can only undo it if you've got the private key. They can do other things as well with asymmetric cryptography. You do digital signing, and that's where you guarantee you sent the message. And you can also do symmetric key distribution. So that is how we share our keys to do symmetric cryptography for something like AES 256. And that is commonly an algorithm called ECDH, elliptic curved key element. Some of you are familiar with it. Which is better, asymmetric or symmetric? Well, asymmetric methods are quite slow to do, but it's quite easy to kind of share the keys because you've just got a public one you share with everybody. Symmetric methods of encryption are very fast, which is great, but it's quite hard to get the keys to people in the first place. So there we have a problem. And also, we now have the problem that quantum computers, not just yet, but we're currently at quantum computers of the equivalent of normal computers in the 50s, 60s. Then those keys aren't going to be safe anymore, and we need some other ideas. So they're usually one of 2 different things. We can find a new hard-to-solve maths problem, which is an asymmetric method, or we can use the weirdness of quantum physics that gave us that before to try and find another way to share information. And that's kind of a new approach, and that makes symmetric keys. So let's look at the maths problem one then. This approach is called post-quantum cryptography, or PQC, and it's the one that you've probably heard most about in the news, I would imagine. And lots of the maths problems that these people have come up with are very, very difficult to set up. They need computers that have quite a lot of memory, and the keys are sometimes enormous, on the order of like a gigabyte, and they need computers with lots of processing power as well to be able to formulate those as well. That the gigabit isn't true for all types of key generation in this sense, but it is for some of them. It's also very, very difficult to prove that they are secure, especially secure against quantum computers, because if you can change the problem into a search problem, then it might be something that can be solved. So it kind of means that it might break at any time. We just don't really know. NIST in the USA, they ran a competition to find the best one, and they were only able to find one that they thought might work. It's called Kyber. They've recommended it, but tentatively. There was about a couple of months ago, there was a paper that came out by a guy called Yeli Chen, and he basically was like, I've been able to break Kyber with a quantum computer, and everybody panicked. It was absolute chaos in, all of the forums, you can imagine all of the stress and excitement about it. It turns out there was a bug in the code, but so it didn't work. It wasn't a real attack, but it just demonstrates the fragility of this, really. It's based on lattices. I don't have loads of time, so I'll be very quick with this, and if I lose any of you, I'm sorry, but we'll come back later. So a lattice, basically, you've got a starting point, and you've got a number of points kind of on some axes, a little bit like, graphs, and they're described by some vectors, and then each point is kind of described by some number of vectors. So I've actually got this one. This is 4a, so 1, 2, 3, 4 along, and 2 points up. So far, so good. But you can make that a little bit more complicated. So those vectors that you use aren't necessarily, they don't just have to be the shortest possible ones. They could be kind of long, or they could be really, really, really long, that go all the way up and all the way along. And then that same point is described in a different way. Which is all well and good. And then you can use that to formulate these really difficult problems. So there's lots of different problems. This one, you get given a starting point. You get given a point on that lattice that has some combination of vectors. You don't know what those vectors look like. And then you get given a random point. You have to figure out which one of these dots is closest to that random point. You can look at that and be like, oh yeah, well, I'm pretty sure it's that one. But you don't have the lattice. Mm-hmm. So now what are you going to do? And this becomes really, really difficult when you have your lattices in multiple dimensions. So it's coming out the page. It's also got, another 50 or so other dimensions as well. So another alternative that we have to finding a new hard-to-solve maths problem is using quantum physics. And we can use weird quantum effects to share secret keys. And that's called quantum key distribution. Again, something you might have heard of. It's usually done there's two different ways to do it. I'm going to describe them briefly. But one of those ways uses entanglement. So that is when you've got a pair of quantum particles, like the ones we saw earlier, that if they have been linked together by some way, so maybe you're looking at those two particles through one particular dimension, you've then linked them together. And that means if you give those particles, each one to a different person, if one person changes their quantum, the other one also has to change in response. So what do I mean by that? So we've got this image again. We're looking at it through that dimension into the page. So if the person that has the yellow one squashes it down, then the other one's got to squash it down in response as well. Because this has a finite amount of stuff, which kind of means that it's all got to act in the same place. I don't have a lot of time, so I'm going to speak very quickly. It's very difficult to detect when someone is using this, which makes it very difficult for someone to break in, which is good and bad. It means that it's a lot more secure, but it's very easy to just stop it from working. It's basically a very easy DOS attack. There are some other systems that use the uncertainty principle. I am actually going to skip this very briefly because I don't have a lot of time. But basically you squash it in one way or the other way, and then you encode some ones and zeros, and then you send it over to the other person, and they randomly choose, are they going to measure it that way or that way? And if they are the same, then they get the number out at the end, which is great. But if they choose different dimensions, then this now has to decide which way it's going to be. And it'll be a 0, or it'll be encoded that way 50% of the time, and that way the other 50% of the time. And they can have a discussion with each other afterwards and say, which way did we measure it? And they can get rid of all of these ones when they realise that they didn't measure it in the same way. So that's quite secure. Do using quantum key distribution. Still possible for a third person or you to come along and try it. It's also really, really difficult to make these things. So they only really work in special conditions, short distances, that kind of thing. So we're very unlikely to use them in practice. So what are we going to do? Because these are so difficult to make, the goal really for a lot of people is to take Kyber and roll it out into as many things as possible. But there are obviously lots of people who are very worried that it's actually not all that secure. And it might be better, it might not even be better than what we have already. So lots of people are recommending hybrid. So you roll this out in conjunction with existing cryptography so that you kind of have a backup there, if you like, so that the two methods are used together. Ideally, we'd have a better solution. So I said that I spent some time doing research. I'm going to talk about this again very briefly because I don't have a lot of time. But we came up with an alternative to that, and it's nearly quantum key distribution. So it's kind of the same stuff as quantum key distribution, but without any of the physical hardware, and it's using that probability theory side of it and none of the actual quantum physics. So we can replicate that probability theory in a purely software-based method. And we didn't really understand how it worked until very, very recently, but it's a way of doing symmetric key. I think I've got a few minutes, so I will go through it. So basically, you have one person, they start off with a lot of random numbers. So this person, Alice, they flipped a coin, got 50-50 heads and tails. And then what she's going to do, a bit weird, she's not going to tell anybody, she's going to make some deliberate mistakes in those numbers. So she's flipped some of these coins here. She's not going to tell anybody where she's done that. But she's going to keep that quiet, and we've kept it red here so that you can see which ones were the ones that she flipped. She sends that over publicly to Bob. He goes, okay, thank you very much. And he also makes some deliberate mistakes. At random, he's also not going to tell anybody where he's done his mistakes. And in some places, he's just introduced a new mistake. And in other places, Alice still has her mistakes. But there are some places where Alice has made a mistake, and then Bob has undone it again. And he has a head here, and she has a head here. But publicly, all you could see was a tail. And nobody else that's seeing this communication has any idea where those mistakes have been made. And so what you've got here is purely by probability, you've introduced some completely secret numbers. There's another step that you need to do, so we'll have some mistakes that are still left in there. And so what we can do is we can break those numbers up into blocks. So the example I've used here is 2. And then we can share some kind of summary information that doesn't disclose the specifics of what's in there, but just a summary. So, for example, the parity, that's, is it an even number of heads or an odd number of heads? And if they have the same parity, they can go, there's a really good chance we've got a match here. And we definitely made a mistake if it's the wrong parity, so we'll get rid of those ones. They have to repeat this process a few times, because you have some, like this first example here, where they've just managed, just by chance, to make 2 mistakes. So you have to repeat it a few times. What you end up with is a list of completely matching keys, and as long as you've got some of those purple ones in there that were kind of a mistake that Alice made and then Bob undid it, then you've got some secrecy. Final thing to do is perform a hash. If you don't know what a hash is, basically you kind of multiply every number in here by every other number in there, which means that you need to know all of the numbers to be able to figure out what that end bit is there. So that secrecy is kind of distributed along that number. So now they have some matching keys, which is great. So this might be the next step towards a quantum safe world. We certainly hope so. This is what AI thinks that it's going to look like. If any of you are developers, or if any of you are particularly mathsy and kind of interested in knowing more how this works, come and speak to me, because we are, since we got investment yesterday, now looking to do our more stuff with this. So if anyone's interested in kind of testing that out, let me know. And just to summarise, we started off at the start understanding a little bit about classical stuff and traditional cryptography. Then we learned a little bit about quantum, which is the smallest finite amount of stuff possible. We showed how you can use that to solve new maths problems with a quantum computer, including prime factorization, which breaks existing cryptography. So we talked about how people have come up with new maths problems, such as the lattice problems to create post-quantum cryptography. And we heard about how NIST have put on a competition for that, and how Kyber is the current leader. And we've also talked about quantum key distribution, which is another method of doing that. It's just very difficult to do. And finally, a potential new alternative to that as well. So thank you all very, very much.